All right, let me start with a little puzzle that ought to bother you because it bothered me for years and I'm still not sure it's done bothering me. You rub a balloon on your sweater. Nothing dramatic, no sparks, no thunder, no explosion, just a balloon, and yet after this gentle little rub, the balloon suddenly has opinions. It wants to stick to the wall. It wants to chase your hair. It behaves as if it has developed a personality, an attraction, a preference. And the wall, which moments ago had no interest whatsoever in balloons, now seems oddly receptive. Now here's the paradox. If I asked you what is causing this, you might say electricity. Fair enough. But that word doesn't explain anything. It just labels our confusion. Because what actually happened? Did something move? If so, what? Did something flow from the sweater to the balloon? How did the wall get involved? And perhaps most irritating of all, how does the balloon know the wall is there before it touches it? That's the part that should make you uneasy. Because whatever electricity is doing, it's doing it across empty space. No contact, no touching, no obvious messenger running back and forth carrying notes. If you think about it carefully, it's outrageous. Imagine you and I are standing across the room. I suddenly reach into my pocket, rub a balloon, and without throwing anything at you, you feel a force tugging on your sleeve. You'd be perfectly justified in calling the police or a psychiatrist. Yet when electricity does the same thing, we nod politely and say, ah yes, electric forces. Here's where things get strange. Gravity does this too. Magnets do it. But electricity does it better, stronger, faster, more precisely, and with an attitude. It repels when gravity only attracts. It switches signs, plus and minus, like an unlike. It's as if nature said, let's make one force that behaves sensibly, and another that keeps flipping the rules just to see who's paying attention. So you might think, all right, maybe there's something between the balloon and the wall, some invisible stuff, a mist, a stretchy rubber sheet. People love rubber sheets. But the trouble is, whenever you try to pin this stuff down, it slips away. You can't bottle it. You can't scoop it up. You can only describe what it does. And that's already a warning sign in physics. You see, when we really understand something, we can usually say what it's made of or how it moves. Air, molecules bouncing around, water waves, water going up and down, sound, pressure variations. But electricity, the moment you think you've got it, it pulls another trick. Here's another irritation. If you charge one object and bring another nearby, the force doesn't wait. There's no noticeable delay. It's as if the information travels instantly. But that can't be right because nature has a speed limit. Nothing outruns light, not even electricity, no matter how impatient it seems. So already we're in trouble. We have a force that acts across space, doesn't seem to need contact, behaves differently depending on sign, and appears to know things faster than it's allowed to know them. And we haven't even plugged anything into a socket yet. When I was younger, much younger, I thought maybe adults knew what electricity really was, and they were just simplifying it for us kids. You know how grown-ups do. But later I discovered something alarming. The grown-ups were simplifying it for themselves, because at the bottom the explanation always stopped at the same place. That's just how electric charge behaves, which is another way of saying, we don't know why, but we can tell you the rules. Now that's not nothing. The rules are fantastically accurate. They work so well we can build radios, computers, and machines that fit in your pocket and argue with you. But accuracy is not the same thing as understanding. A parrot can recite the multiplication table. It doesn't mean the parrot knows arithmetic. So let me give you a thought experiment, one that looks innocent but isn't. Suppose you have two tiny charged particles far apart in empty space. Nothing else, no air, no wires, no ether. Just the two charges staring at each other across the void. They repel or attract depending on their sign. Fine, but here's the question. What exactly is doing the pushing or pulling? Is one particle sending out something? If so, what carries it, and how does the other particle receive it? Does it absorb it, bounce it back, keep a receipt? Or, and this is even stranger, does each particle simply know the other one exists and adjust its behavior accordingly, like old friends who don't need to talk? If that last idea makes you uncomfortable, good. It should. Because once you allow particles to just know things, you've given up on explaining anything at all. You might as well say the universe runs on gossip. The deeper you go, the more electricity starts to feel like a magician's act. The equations are clean, elegant, beautiful, but behind the curtain, the mechanism is suspiciously abstract. Fields, potentials, lines of force drawn on blackboards as if nature herself were sketching diagrams for our benefit. And yet, this is the part I love, we can feel electricity. A shock, a spark, a hum in a wire. It's not some distant cosmic mystery. It bites, it lights your room. It makes your heart beat properly if it's behaving, and improperly if it isn't. So we're stuck with a force that is intimate and immediate, yet conceptually slippery. It works perfectly while refusing to tell us what it really is. That combination, reliable and mysterious, is dangerous. It tempts us to stop asking questions. But if there's one thing electricity teaches us, it's that nature doesn't owe us comfort. It only offers consistency. And even that comes with a sense of humor, because the more carefully we look at this simple idea, charge here, force there, the more we realize that what's actually moving, what's actually changing, might not be the objects at all. It might be something subtler, something spread out, something that only exists when you try to measure it. And once you start thinking that way, the balloon and the wall are no longer a child's toy. They're a clue, a warning, an invitation. If you're curious enough to follow it, say the word and we'll keep going. Good, because once you agree to keep going, you've already stepped into the mess, and there's no polite way back out. So let's return to that balloon, because it's doing something astonishing while pretending to be ordinary. You rub it, and suddenly it can rearrange the behavior of the world around it. That ought to make you suspicious right away. Ordinary objects don't do that. A rock doesn't convince a wall to come closer. A shoe doesn't persuade your hair to stand up and salute. Something new has entered the story. People often say, electrons move from the sweater to the balloon. All right, fine. Let's accept that for the moment. But don't relax yet, because now you've only pushed the problem down one level. What is an electron doing that makes everything else reorganize itself? Imagine I give you a crowd analogy. Suppose you're at a party and someone famous walks in. Suddenly people rearrange themselves. Clusters form. Others back away. No one touched anyone yet, but the room reorganized anyway. Now, in that case, the explanation is easy. People can see, think, anticipate. They have information channels. Eyes, ears, gossip. But electrons don't have eyes. They don't read magazines. And yet they behave as if they are exquisitely aware of their surroundings. Here's a simple experiment you can do in your head. Take two identical metal spheres on insulating stands. Touch one with a charged rod. Now the sphere is charged. Bring the second sphere close, but don't touch it. Instantly, charges inside the second sphere rearrange themselves. The side closer to the first sphere becomes oppositely charged. The far side becomes similarly charged. And all of this happens without contact. So the electrons inside the second sphere somehow receive the memo. Something charged is nearby. Adjust positions accordingly. How did they get the memo? You might say, an electric field. That's the standard answer, and it's a good one as far as it goes. But notice what we've done. We've introduced a new character to explain the behavior, a field that exists in space even where there are no particles. This is already a radical move. Empty space used to mean nothing. Now it means something that can carry energy, momentum, instructions, and occasionally a nasty surprise. The electric field is like a set of invisible instructions written everywhere in space. If a charge shows up here, this is how it should move. That's a strange sentence when you stop to think about it. Instructions without an instructor. Rules written with no paper. To make this less ghostly, people draw field lines. Little arrows pointing away from positive charges and toward negative ones. It's a wonderful picture. It helps you think. But you mustn't take it too literally, or you'll imagine tiny spaghetti strands tugging on electrons, which isn't quite right either. The field isn't made of lines. The lines are made of chalk. What's real, if we dare use that word, is the pattern of influence. If you put a charge here, it feels a push that depends on where it is relative to other charges. The field is our bookkeeping device for that fact. Now let me try another analogy, one that almost works and therefore must be handled carefully. Think of space like a financial market. The moment some big investor makes a move, prices everywhere shift, not because something traveled physically from one stock to another, but because the conditions changed. The rules of interaction updated everywhere at once, except this analogy breaks in an important way. Markets rely on information traveling through people and computers. Electric fields don't. They're already there, waiting. In fact, that's one of the most unsettling things about electricity. The field exists whether or not anything is using it. You can clear all the charges out of a region of space, and the field can still be there, humming quietly, ready to shove the next charge that wanders in. So now the question becomes even sharper. If the field is real, what is it made of? Does it wiggle? Can it move? Can it store energy? The answer is yes, yes, and yes, and now we're really in trouble. Because once you admit that the field carries energy, you've promoted empty space to a kind of physical substance. Not a material you can scoop up, but something with weight in the accounting books of the universe. You can charge a capacitor, two metal plates separated by nothing but air or vacuum, and store energy in the space between them. Not in the plates, in the nothingness. And if you're not careful, that nothingness will release the energy very suddenly and remind you it was never really nothing at all. Here's where intuition starts to wobble. We're used to thinking that energy belongs to objects, a moving ball, a hot stove, a stretched spring. But electricity cheerfully stores energy in patterns, arrangements, relationships. The energy isn't on the charge. It's in the configuration of charges and fields together. Change the arrangement, and the energy changes, even if no particle budges an inch. That's a very modern idea, whether you like it or not, and it leads to a curious consequence. If the energy is in the field and the field can change, then changes in the field must propagate. They can't happen everywhere at once. This rescues us from the embarrassment of instant communication. If I jiggle a charge over here, the field near it changes first. Then that change travels outward at a definite speed, the speed of light, updating the instructions as it goes. A distant charge doesn't respond to what I did now, but to what I did a little while ago when the news finally arrives. Electricity, it turns out, is patient after all. It just hides the delay very well. But notice how far we've gone from the balloon. We started with a child's trick and ended up with space behaving like an elastic accounting system for cause and effect. And we still haven't answered the most annoying question. Why does a charge respond to the field at all? You can say, because that's the law, and that's true. But it's not satisfying. It's like saying a piece of music sounds good because that's how the notes go. At some point, physics always hits a bedrock where explanation turns into description. Electricity reaches the bedrock faster than we'd like. The rules are simple to write down, but impossible to visualize completely honestly. And yet, and this is the part that keeps me smiling, we can play with these rules. We can predict absurdly subtle effects. We can build machines that exploit the field's quirks with surgical precision. We can make light itself by shaking charges just right and letting the field do the rest, which suggests that even if our pictures are imperfect, we're touching something real, something that doesn't care whether we understand it, only whether we respect its consistency. And once you accept that, a new kind of curiosity opens up, because now the question isn't, what is electricity made of? But what kind of universe allows relationships to be more fundamental than things? That's where the story starts to bend back on itself, toward equations that behave like poetry and paradoxes that refuse to stay quiet. If you want to follow that thread a little deeper, say the word. All right, let's lean into the discomfort, because this is where electricity stops being merely strange and starts being genuinely mischievous. By now we've accepted grudgingly that the electric field is the thing doing the work. Charges respond to it, energy lives in it, changes crawl through it at the speed of light. Fine. But there's a detail hiding in plain sight that, once you notice it, refuses to leave you alone. The field doesn't just tell charges where to go. It tells them how fast to change their motion. That's already peculiar. Forces don't just cause motion, they cause acceleration. So the field is not merely nudging charges along like a gentle breeze. It's dictating the curvature of their future. That's a very strong influence for something you can't touch. Now here's a curious thing you can try in your imagination. Take a single electron all by itself, floating in empty space. No other charges, no fields, no walls, nothing. What does it do? Absolutely nothing. It just sits there, no drama, no buzzing, no sparks. Electricity, it seems, requires company. It's a social phenomenon. The moment you introduce another charge, however distant, everything changes. Suddenly the electron has a future with structure, a direction, a tendency, and that tendency is encoded not in the electron itself, but in the space between the two. This should already make you uneasy, because we've been trained to believe that the properties of a thing belong to the thing. Mass belongs to the particle. Charge belongs to the particle. But the behavior, the meaning of the charge belongs to the relationship. Now let me push this one step further, because this is where people usually blink. Suppose you accelerate a charge, shake it, jiggle it, wiggle it back and forth. Something new happens. The field doesn't just adjust, it radiates. Ripples peel off and race outward. Those ripples are light, not metaphorically, literally. Light is what happens when electric fields can't keep their secrets. That's already delightful. The same force that makes a balloon stick to the wall is responsible for rainbow sunsets, radio waves, and the glow of your screen. It's all electricity refusing to sit still. But here's the catch. When a charge emits radiation, it loses energy. You can measure this. The field carries the energy away. But now ask yourself, when does the charge pay the price? If the energy leaves and travels outward at the speed of light, then the charge must begin losing energy before the radiation reaches anything else. So the charge is reacting not to the future, but to its own changing field. In other words, the electron is responding to itself. That's not a philosophical statement. That's a mathematical nightmare. You see, when you write down the equations that describe how charges move in response to electric fields, everything works beautifully, as long as the field is caused by other charges. The moment you include the field generated by the charge itself, the equations start to misbehave. Infinite forces appear. Predictions explode. The math starts shouting at you. Nature, it seems, does not enjoy being asked how a thing pushes on itself. Physicists have spent decades tiptoeing around this problem, inventing clever tricks to subtract infinities and keep the answers sensible. The tricks work, but they feel like stage magic. Necessary, effective, and slightly embarrassing. And this is one of the reasons electricity still baffles us. It works perfectly as long as we don't ask certain questions too loudly. Now let me tell you something amusing. If you take Maxwell's equations, the beautiful set of rules governing electric and magnetic fields, and look at them just right, you'll notice they don't actually mention charges as the primary actors. They describe how fields change in response to fields. Charges sneak in as sources and sinks, but the real drama is in the fields talking to themselves. In fact, if you're feeling bold, you can imagine a universe where fields exist first, and particles are just places where the field does something especially interesting. Knots, twists, persistent disturbances. That idea is not science fiction. It's a serious proposal, and it flips the story completely. Instead of saying, charges create fields, you say, fields create the illusion of charges. Whether you like that picture or not, and you don't have to, it solves a certain aesthetic problem. It makes the field the main character, and particles the supporting cast. But it introduces a deeper puzzle. If fields are fundamental, then what is space itself? Because fields don't float in space like fish in water. They are attributes of space. Change the field, and you've changed the state of space. So now space is no longer an empty stage, it's an active participant, a medium with rules, memory, and tension. At this point, you might feel like we've drifted very far from the wall and the balloon. But we haven't. We've just followed the thread honestly. Here's another counterintuitive truth that electricity insists upon. The force between charges depends not only on where they are, but on how they're moving. Two charges moving side by side behave differently from two charges at rest. The magnetic field enters the picture, not as a separate force, but as electricity seen from a different frame of motion. This is one of those moments where physics smiles slyly and waits for you to catch up. What we call magnetism is electricity wearing a disguise. Change your perspective, move alongside the charges. and electric forces morph into magnetic ones. No new phenomenon required, just relativity doing a costume change. So electricity isn't just a force, it's a lesson in humility. It tells you that what you see depends on how you're moving, that the universe doesn't commit to a single description unless you force it to, and this leads to an extraordinary realization. The electric and magnetic fields are not separate things. They are components of a single entity stitched together by the geometry of space-time, which means that electricity is whispering secrets about time itself, because once time joins the story, causality becomes delicate. Fields don't just depend on where charges are, but where they were. The influence you feel now is a message from the past, encoded in the field's structure. So when a charge responds to an electric field, it is, in a very real sense, responding to history. That's a remarkable thought. Every electric force you feel is a conversation with the past, delayed just enough to preserve the universe's bookkeeping. And still, we haven't answered the simplest question of all. Why does a charge respond to the field with the particular strength that it does? Why this charge, this mass, this coupling? Why does nature choose these numbers? We can measure them to absurd precision. We can predict outcomes to 10 decimal places. But we cannot derive the values from anything deeper. They are inputs, facts, declarations. Electricity works because the universe says so. That's not a failure of physics. It's a boundary. And boundaries are interesting places to stand. Because once you see how much structure, beauty, and coherence arises from these few stubborn rules, you begin to suspect that understanding may not mean reducing everything to something simpler. It may mean learning to live comfortably with a small number of irreducible mysteries. Electricity is one of them. Not because it's complicated, but because it's too simple in a way that leaves no room for explanation underneath. And that realization, quiet, unsettling, and oddly liberating, starts to shift how you look at everything else.